let's suppose we have a string and a bob attached to something like, let's say, a ceiling. So we have a ceiling, we have a string, and we have a bob. Now what we commonly assume in this situation is that when we have this, is that this string here, the path or the axis formed by this string is perfectly vertical. So what this means is that if we have a ground, if we have our Earth's ground here, and we extend this axis through the center of the bob, continued from the string, it's going to form a right angle with the ground. And what this also means is that if we extend this line further on, and we're going to have, and here it's the center of the Earth. I know it doesn't look like it, but anyways, what we assume is that the axis formed by the string is going to touch the center of the Earth. Now, here's a question, and here's what I'm going to debunk today in this video. And what I'm going to debunk today is that the axis formed by the string is in fact not vertical. And so, in other words, if we extend the axis formed by the string, it's not going to touch the center of the Earth. And why is that? Well, the answer to why this is the string is not a vertical line is because of the rotation of the Earth. And so, what does it mean by the Earth rotating? It means that everything on the surface on the Earth also rotates. And so, if you have our Earth here, so yeah, this is our Earth, and let's say this is the North Pole and the South Pole. We know that the Earth is spinning in this direction, or in some direction. And so, let's say if an object is here, it's going to be moving in a trajectory that looks something like that, and towards the back, and back again like that. And an object here will also be moving in a similar form. So it's going to move in that direction, and back, and then again, and make a circular path. And so the only two places that an object will not rotate with the Earth will be the two poles, because in these two poles, because those are crossing the axis of rotation, those objects are not going to be moving, and the objects located on the equator are going to be moving the most. And now, using this law, we could somehow formulate how we could calculate, for example, the axis made by the string, and the real axis, or the string axis and the real vertical axis that in fact does cross the center of the Earth. So today, the aim of today's video is to figure out what angle alpha is, to formulate angle alpha on anywhere on Earth, on any location on Earth, with regards to the angle that an object forms with the center of the Earth, which we call the latitude. So the aim of today's video is to formulate alpha, the difference between the real vertical axis and the string axis, in terms of theta, the latitude in which the object is located on Earth. Okay, so that's our aim. So now, to calculate or formulate that, let's draw another diagram and see the forces acting on the object. So we have our Earth, which is a circle. We have our center of the Earth. And let's say we have our object, our bob, our circular bob, located somewhere here. This is our bob, and this is our bob. And we have our string, which is like that. I'm going to draw a string later on. I'm just going to draw the bob first. Firstly, what we know is that there's, as I said before, there is the object, the bob, is rotating around the Earth. And what does it mean by the bob rotating around the Earth? Well, it means that it has some kind of resultant force. So let's say when we draw a force diagram of a bob, what we tend to do is say we have weight, we have tension, and these are equal in magnitude, and so the bob, there's no resultant force acting on the bob. This is what we commonly do for a stationary bob. When we hold a stationary bob with a string on our hands. We have tension, we have weight, these two are equal in magnitude, so there is no resultant force. What we said in fact is that the bob still has some kind of resultant force because it is moving. It is moving around the earth, so it is not stationary. There is some kind of resultant force that's towards the center of its circular path acting on the object. And so this is not the case. And in fact, what the case is that there is a resultant force in this direction. And the reason why it's in this direction is because the path forward. So when we say this is our north pole here, and this is our south pole here, and say this is our axis of rotation, the Earth is going to be spinning. And so the circular path formed by this bob here, located here, is going to be around this path. And so the center of its circular path is in fact going to be here. This is going to be the center of the circular path of the bob. And so that's our resultant force, annotated by sigma f. That's going to be our resultant force. Now what do we also know? Well, we all know that to make that resultant force, there are only two forces acting on the bob, which is, first of all, our gravity, so our weight, force of gravity, or let's just say mg. So m here is mass of bob, and we're assuming that the string has no mass, of course. So this is our force of gravity. And what we also have is our tension force. And what we know about our tension force is that because there are only two forces, our weight and our tension force acting on the object, those two forces must resolve to give our sigma f. So in magnitude, it's going to be something like that. So this is going to be our tension force, Ft. And Ft, we know acts here, so it's going to be, something like that. And these two are, of course, equal in magnitude because these two are the only forces acting on the bob. So our force of tension, which when for a resolving diagram looks like that, is here. And the aim of today's video, as I said before, is the difference in angle between the real axis and the true vertical axis and the string axis. And so the string axis will be parallel to the direction that our tension force is directed towards, because it's the string. The tension force originates from the string. And so what we could say, and what we also know is that because that our weight force is parallel to our true vertical axis, because weight is directed towards the center of the earth. And so if this is our weight, if we extend this axis, we could say this here is our alpha. So this angle here is what we're trying to calculate. And now we have some other variables. We have one other variable, and that variable is our latitude, which is theta. And so let's say we know that theta is our latitude. So if we have this over here, here's the equator. We're going to have this angle here as theta. And yeah, so let's define our thing. So we have theta is latitude. We also have G, which is gravitational field strength at surface of Earth. And yeah, so and that's basically it. That's all we have to know about the forces acting on the bob here. Now, before we do anything, let's set up our diagram more clearly. So we have the bob. We have our bob. We have this force, which is weight, acting towards the center. We had our resultant force, and we had our tension force. And we said that our weight force plus the tension force resolves to the resultant force. And so, and what we also know is that because when we have our tension force over here like that, and extend this axis, because we know that this here is alpha, which is what we're trying to find. This angle here is also going to be alpha because these two are parallel lines, and this is extended. And what we also know is that because this here is theta, we know that when we draw this imaginary line, right angle, this here is also going to be theta, and that's delta F. That's sigma F, that's our tension force, and that is mg. And so looking at this diagram, we could come up with two equations. First one looking at the vertical axis, the second one looking at the horizontal axis. So the first one, when we're looking at the vertical axis, we know that the vertical component of Ft is equal to the vertical component of mg, because delta F in this perspective, delta F does not have any vertical component because, as I said before, it's directed toward the Earth spins in a horizontal path. Let me assume this is vertical, and so there's delta F, or sigma F does not have any vertical component, and so the vertical component of these two forces must be equal, and the vertical component of Ft would be Ft sine of this angle, which is theta plus alpha. So Ft sine of theta plus alpha is going to be equal to mg sine of theta, because mg is only has this angle over here. And so that's what we know from the vertical axis, and from the vertical perspective, and from the horizontal perspective, what we can know is that, well, now we have Ft of cosine theta plus alpha, which is this over here, plus delta F, which is this, so equal to that. So plus sigma F, the resultant force is equal to mg cosine theta, which is, this is our mg, so that's our mg cosine theta. So these two basic equations are all we need to solve for alpha. But before that, we know that our resultant force, sigma F, is directed towards the centripetal direction. And so we could use our known formulas to calculate an expression or give an expression for sigma F. And so let's do that before we calculate anything else. So let's say that's done, so could erase that. So we have our resultant force, which is directed towards the centripetal direction, is equal to mv squared over r, because it's a famously known formula, and which originates from mass times acceleration, and the resultant force is equal to mass times acceleration, and acceleration is v squared over r. And now we know n, but we don't know v and we don't know r. So let's do that now. Well, v, first of all, v is 2 pi r over our period. And what we also know is that, our period here is going to be 1 day, which is going to be 24 times 3,600 seconds, because that's the length of 1 day. But to make it simpler, I'm just going to say this is equal, because 2 pi over t is equal to omega, which is our angular velocity. I'm just going to use that value because, again, 2 pi over t is also a constant. So to make this question, or to make the expression simpler, I'm just going to say omega is equal to 2 pi over t, which is equal to 2 pi over 24 times 3,600, and that is a constant. And so our velocity is omega r, or r omega, it doesn't really matter. And plugging that into this equation, we have delta F is equal to m times omega squared r squared over r, which is equal to m omega squared r. Now, but we still don't know our expression for r, because r is this length over here, the radius of our circular path. R is not the radius of the Earth, because the radius of the Earth is this line over here. But because we know this is our radius of Earth, which is a constant, so radius of Earth is 6,371 kilometers, or 000 meters, and that's a constant. We know that value, and so I'm also going to use this expression over here, RE. And what we know from this diagram over here, although it's a bit messy, we know that this is R, and the hypotenuse, you can see that the horizontal line is R, the hypotenuse is RE, and we could maybe take R down to here, this axis, this here is theta, and so we can know that R is equal to RE cosine of theta. So R is equal to RE, radius of Earth, cosine of theta, which is all composed of our known values or variables. And so we could say that m omega squared R is equal to m omega squared RE cosine theta, and that's our value for sigma f. And so rewriting our two equations, well, our first equation is same. It doesn't have any sigma f involved in it, but looking at the second equation, we could say that ft cosine of theta plus alpha plus our sigma f, which is this here, so m omega squared RE cosine theta, m omega squared RE cosine of theta is equal to mg cosine of theta. And so these are the two equations that we have so far. And these two equations are all we need to derive an expression for alpha. So now, erasing our diagram and all that, that's all done. So we have these two equations, and I'm gonna write it a bit neater. So let's say we have first equation, ft sine of theta plus alpha is equal to mg sine of theta, and the second equation, ft cosine of theta plus alpha plus m omega squared RE cosine theta is equal to mg cosine theta. Now, the way I'm going to solve this is I'm first of all going to look at the first equation, and the reason is the first equation does not have anything else other than theta and mg involved in it, and m and g are all constants, and so you could say from the first equation what I could do is derive an expression for ft, and that's easy. We divide both sides by sine of theta plus alpha and get ft is equal to mg sine of theta over sine of theta plus alpha. So that's basically our expression for ft. And then plug in this expression here into the second equation. We're gonna have mg sine of theta, and the numerator multiply cosine of theta plus alpha, then over sine of theta plus alpha. And that's going to be and plus m omega squared RE cosine theta is equal to mg cosine theta. Now all terms here have m in it, so we don't need it. So let's cancel m out, and we basically have this equation over here. Now we have what we know about cosine theta over alpha over sine theta over alpha is that it's going to be equal to the reciprocal of tangent of theta plus alpha, or the cotangent of theta plus alpha. And so what we could do is move the tangent to the denominator because it's the reciprocal, and get an expression for tangent of theta plus alpha, which is going to be really convenient. So we have this here is going to be tangent theta plus alpha over 1, or 1 over tangent of theta plus alpha. So we have g sine theta over tangent of theta plus alpha, and that's equal to g cosine theta minus omega squared RE cosine of theta. And we could say that conveniently we could wrap this and that to g minus omega squared RE of cosine of theta. Now then what we could also do is divide both sides by g sine theta to get an expression that is fully about tangent of theta plus alpha, because what we're trying to do is isolate alpha. That's our goal. So I'm going to do my best to isolate tangent of theta plus alpha first. And so dividing both sides by that, we have 1 in the numerator and have g sine theta over there. And again, we have cosine theta, cosine theta divided by sine theta would be 1 over tangent theta. So do that and have this here as tangent of theta. And then what we have is when we then reciprocal both sides of the equation, we have tangent. We're going to have tangent of theta plus alpha is going to be equal to that this here in the numerator. So g tangent of theta over g minus omega squared re. Yeah, just that. G minus omega squared re. And now, because we have an expression for tangent of theta plus alpha, we could easily obtain an expression for well, let's do it this way. So first of all I'm gonna expand tangent of theta plus alpha first. So we know that by the I don't know, tangent summation rule, I don't know. But anyways, we know that tangent of theta plus alpha is equal to 1 minus tangent theta times tangent alpha. In the denominator and the numerator, we have tangent theta plus tangent alpha. So we have tangent theta plus tangent alpha over 1 minus tangent theta tangent alpha is equal to this expression over there. And because what we want to do is isolate alpha. First of all, I'm gonna multiply the denominator in both sides, and so I'm gonna have 1 minus tangent theta tangent alpha, and have that gone. And then subtract tangent theta in both sides to get tangent alpha is equal to g tangent theta g minus omega squared re times 1 minus tangent theta tangent alpha minus tangent of theta. And then we have, well, this here is a bit annoying. So first of all, I'm going to expand everything. So we have g tangent theta. So first of all, multiplying by 1, we have, well, itself unchanged. And then we have minus that times that. So we're going to have, I'm going to say plus and have the sequence changed, because pluses are always easier, always better. So we have omega squared re minus g, then we have g tangent theta, and that times tangent theta would be tangent squared theta times tangent alpha, and then minus tangent theta. And finally we have, because this here contains tangent alpha, we're going to move this to this side. So we have tangent alpha of that here, so 1 minus that over here, but again we don't like the minus, so we have plus g minus omega squared re over g tangent squared theta that's equal to g tangent theta over g minus omega squared re minus tangent of theta. Now we don't like these 1 plus and that minus that, so what I'm going to do is unify the denominators of these expressions before I go on to divide both sides by the bracket over here. So I'm gonna do that. I'm gonna erase. I don't have space. I'm gonna erase this side over here. And hopefully that's gonna be the last time I erase. So from this here, we have so we have 1 plus that. So it's going to be tangent theta times. So because it's 1 plus, we have g minus omega squared re plus g tangent squared theta. So we have g minus omega squared re plus g tangent squared theta on the numerator, and have g minus omega squared re as it is. And that's going to be equal to g minus omega squared re, and in the numerator we're going to have g tangent theta as it is, and have minus tangent theta times that, so minus g tangent theta, and you can see these two cancel out, but then have plus omega squared re tangent theta, so plus omega squared re tangent theta, and as you can see these two cancel out, so we have finally tangent theta then is going to be equal to, first of all, we're dividing both sides by this expression over here, this inside the bracket, so we have omega squared re tangent theta over g minus omega squared re times, so reciprocal, we have g minus omega squared re over g minus omega squared re plus g tangent squared theta. And as you can see, these two cancel out, so we have, wait, yeah, that's here, that's tangent alpha, right? Yeah, that's what we're trying to find. So because tangent alpha, we're using tangent alpha, not tangent theta. And so we have tangent alpha finally is equal to omega squared re tangent theta over g minus omega squared re plus g tangent squared theta. Now, one thing we could do is we could say that's equal to, well, the same numerator, and wrap g and g tangent squared theta by 1 plus tangent squared theta. And because we know that 1 plus tangent squared theta g minus omega squared re, we know that that here is equal to secant squared theta, because sine squared plus cosine squared is 1, and so dividing both sides by cosine squared, we have tangent squared theta plus 1 is equal to secant squared. So we have that secant squared, so we have finally our alpha is going to be arctangent both sides. We're going to have secant squared theta, well, g secant squared theta minus omega squared re, and the numerator we're going to have omega squared re tangent theta. And that's our final expression for alpha. And in case you forgot, what was our alpha? It's when we have our Earth here. Oh, basically, well, moving on to, the visual world, I say. When we have a ceiling and our string here. Our string will never be vertical unless you're in the North Pole or the South Pole. And it's going to be slightly tilted by an angle that you won't realize, but it will be there. And so alpha is basically when we have the true vertical axis, and that's here's the string. That here is our alpha. And as you can see, our alpha is equal to arctangent of omega squared RE tangent theta over G secant squared theta minus omega squared RE. And the values of these expressions are as follows. So we have omega, which is our angular velocity of the Earth, so 2 pi over 24 times 360, 100, and 3600. And we have G, which is our gravitational field strength on surface, theta, which is our latitude. So for example, if you're at here on Seoul, I reckon it was something like 37 point something. Yeah, it all depends. But unless your latitude is 90 degrees, which is the North Pole or the South Pole, we're gonna have some kind of alpha. So every time you hold a string attached to something heavy, always realize that that string is not vertical, and it's always gonna be slightly tilted from the true vertical axis. Yeah, that's the conclusion of today's video. I hope you enjoyed it. And yeah, every time you have a string, just keep in mind that it's not vertical. Thank you.